This is a GraphQL query that searches a list of rewards, ordering them by the partner's English name, selecting 10 beginning after a specific ID, and returning the nearest location for each partner out of a table containing almost 50,000 locations. This is a query that returns a list of all locations within 10 kilometers from the user, accompanied by the distance from the user to that location, and partner details that would be appropriate to display in a card on a map when the user hovers over the location, including partner name, logo, and website information. This is a query that returns translated details for one partner and all their rewards in Spanish, Simplified Chinese, and Traditional Chinese. All three queries took 200 milliseconds or less to execute. The API that I'm querying is the 8x8 Partnerships API. 8x8 is an organization I've been volunteering with for some time now, whose mission is to put an end to hate against the AAPI community by using technology to drive electoral engagement and civic participation. The Partnerships API is intended to strengthen businesses owned by AAPI members and allies, while at the same time offering incentives for getting involved in the political process through our applications. The presentation will explore several design patterns and libraries for creating hyper-efficient GraphQL APIs through the lens of the 8x8 Partnerships API. As I began talking to stakeholders and thinking about how to design this API, it became apparent that it would have to do a lot of lifting. Our partnerships lead wanted to make sure that we wouldn't need to turn any potential partners away. So the API would have to cater to businesses of all sizes in many locations with various technical capabilities. It would need to be compatible with our existing web app, but it would also need to be flexible enough to be integrated into new applications, as we anticipated replacing our web app with a mobile app in the near future. We also plan to localize the mobile app, so the Partnerships API should expose translated details in any languages we choose to support. The API would need an admin interface, which we can use to update data in the database, which ideally should be able to share type definitions with the Partnerships API itself. Finally, the API must be cost-effective to operate. Reliance on usage-based external services, such as APIs from providers like Google, should be minimized. Based on these requirements, I decided to use the following tech stack to implement the API. PostgreSQL. For the database layer, I decided to go with PostgreSQL. PostgreSQL has a rich extension library, including extensions for storing and querying geospatial data, creating composite indices including geospatial and non-geospatial columns, running tests written with SQL, and much more. Docker. I created and published a custom Docker image, which we use to spin up containers to run Postgres. This image includes PostGIS, an extension for working with geospatial data, as well as pgtap, pgprove, and pg Postgres Anonymizer. Some of these extensions proved difficult to install in Windows, but distributing a Docker image makes this a non-issue. In conjunction with Docker, we use dbmate to run migrations. This allows developers to easily keep their local database synchronized with the latest changes from the upstream repo, and can even let us manage the database with CI/CD pipelines. We can even spin up a separate container just for tests and then remove it once the test suite has run. GraphQL. GraphQL was chosen for the API layer for its flexibility. GraphQL affords client applications the ability to request exactly the information they need, and only that information, making it highly efficient and adaptable. GraphQL is also defined with security in mind. It is idiomatic to limit queries by depth or cost, and introspection can be disabled in production. Finally, GraphQL is very popular, and as a result, a thriving ecosystem of tools and libraries has sprung up around it. TypeScript. This project probably couldn't have been built without TypeScript, as you'll see later. A highly complex type system created by leveraging TypeScript features like mapped and conditional types helps developers keep developers sane as they work through deeply nested tree structures. This project follows a data-oriented approach, focusing on immutable data structures and stateless transformations. GraphQL and database layer schemas are first-class citizens and are defined in their native languages rather than with ORMs or TypeScript libraries. The database schema contains implementation details that can vary based on the nature and capabilities of each partner. For instance, vouchers can be stored as single-use or multiple-use vouchers depending on whether the partner has provided us with batch-generated single-use codes or a single code that they wish to remit to all users. Voucher stubs can be stored for partners with an API that we can reach out to in order to generate actual codes. The database schema also contains tables maintained automatically with triggers that contain only active partners and rewards with translated details in all supported languages, helping us guarantee completeness of data served by the API. Lastly, it contains many pure functions that help us prepare as much data on the database side as possible without relying on back and forth trips from the server to the database. The GraphQL schema presents a unified abstraction of these implementation details. For each entity, translated details can be retrieved in any supported language by providing a BCP47 language tag as a field argument. Lists of entities can be filtered, sorted, and limited, allowing client applications to fetch paginated results. The core challenge in implementing this API was bridging these two schemas. For one thing, each schema is independently quite complex. For another, efficiency can quickly become a problem in GraphQL implementations. The N+1 problem is a well-known issue that presents itself in GraphQL implementations. In many GraphQL implementations, a request is made to the database to fetch parent objects, and then for each nested object, another query must be made to retrieve the details, leading to N+1 queries. Luckily, there's a solution to the N+1 problem. According to Nick Redmark on Medium, the GraphQL Almighty Root Resolver pattern involves using the top resolver to recursively solve the whole GraphQL query, except maybe for calls to external APIs. This can dramatically improve query performance. Instead of N+1 queries, your API will make exactly one. Implementing this pattern requires parsing the info object, the fourth argument received by a GraphQL resolver. This object is a huge tree structure representing every detail of the query. This is the example of an info object from the first query I demonstrated. Naturally, although this solves the problem of efficiency, it makes the problem of complexity worse. Here's where TypeScript really shines. In order to solve this problem, I published 3 open source libraries on NPM. Each plays a role in generating types from your schema definitions to facilitate implementation of patterns like the GraphQL Almighty Root Resolver pattern that might otherwise be too complex to program with certainty about the correctness of the implementation. IntrospecQL is the first of the 3. IntrospecQL connects to your database and reads definitions for tables, views, materialized views, and functions from the PG catalog schema. The PG catalog schema stores metadata about schemas, tables, views, functions, and other database objects. IntrospecQL examines the contents of your database using queries like the one on the left and produces output like you see on the right. It is highly configurable, either with a TypeScript configuration object or using special directives that can be included in Postgres comments. Postgres comments can also be included in the output and converted into tsdoc style comments in TypeScript. IntrospecQL Keysly is an adapter that takes the output of IntrospecQL and formats the types so that they are compatible with the Keysly ORM. In addition to type definitions for tables and views, a special pgfn function is exported that lets you call Postgres functions from TypeScript in a type-safe manner. gclar. gclar stands for GraphQL Almighty Root Resolver, and it's a GraphQL CodeGen plugin. GraphQL CodeGen reads your schema and exposes this information to plugins, which it can use to generate types. In addition to type definitions for your top-level resolvers, gclar creates a special object with methods for reading requested output object fields and arguments from the info object passed to top-level queries in a type-safe manner, granting developers the benefit of IntelliSense and type checking in their code editor as they implement the Almighty Root Resolver pattern. The Partnerships API combines this tool with the Keasley Query Builder and the types generated by IntrospectQL Keasley to construct a SQL query that can resolve the entire GraphQL query at once. Lessons learned and future improvements. Always dig a little deeper. By using the Explain Analyze feature of PostgreSQL, I was able to determine which operators and functions leverage geospatial indexes and how composite indexes consisting of a mixture of columns indexable by a standard B-tree index and geospatial data behaved. It's worth taking the time to find the right tool for the job. Besides GraphQL, I explored the idea of building the API with REST, RPC, and OData. GraphQL took some time to learn, but it was worth it because it fit our use case very well. In the future, I would like to contribute to the PostGIS project. The distance operator calculates distances between geographic points using spherical rather than spheroid math. I looked at the source code, and it seems that the developer tried to get spheroid math to work, but said that they couldn't get it to harmonize with the geospatial indexes. The result is slight inaccuracies around, I think, the equator. For our purposes, the trade-off in speed is worth it, but I would still like to see if I can fix this at some point. Thank you very much.